After this example, you will be able to compute the deflection and moments of unlimited beam subjected to concentrated load. A coal truck is designed to carry a maximum total load of 350 kN on a single axle. The rails are made from steel with a Young modulus of elasticity equal to 200 kN per millimeter squared. The rail geometry is 100 millimeter deep by 50 millimeter wide, and the rails are supported by an elastic foundation with spring constant equal to 15 Newton per millimeter squared. First, determine the maximum deflection, bending moment, and bending stress in the rails. And second, if the truck is designed with two axles 1.5 meter apart, what and where is the maximum deflection? We have two things. The first is to determine the maximum deflection and the moment for single axle, and the second for two axles. To solve this problem, first take single axle truck. In single axle truck, we have just one axle and two wheels. Therefore, if we want to know the force on each rail, we have to divide 350 over 2. Weight on the wheel will be equal to 350 over 2. 350 over 2. This is the load on every rails. First, compute the moment of inertia for the section of the beam. The section of the beam is a rectangle with 50 and 100 depth. BH cube over 12 equal to 15 millimeter times 100 to 3 power 3 over 12 will be 41.67 times 10 to 6 millimeter 4. Lambda will be K, the fourth root of K over 4 EI, gives us 1.456 times 10 to minus 3 per millimeter. Now to compute the maximum deflection. The maximum deflection will occur directly under the concentrated load. Here the beam, this is the beam with section above the section of the beam, and we have, for example, here is the two rail, one axle, wheel at this rail and wheel at this rail. Axle with two wheels, wheel at this rail and wheel at this rail. We have to divide 350 over 2 to get the force at this rail. So we have beam represent the rail subjected to concentrated force. If we want to compute the maximum deflection, we have to use the equation of deflection for points directly under the concentrated load. Under the concentrated load, x will be equal to 0. So when we want to compute the factor of lambda axis, such as A lambda axis, C lambda axis, D lambda axis, all of these factors will be equal to 1. Only B lambda axis will be equal to 0, since it depends on sign. It depends on sine lambda x. Sine lambda x, e to the power e to the minus lambda x multiplied by sine lambda x. Therefore, B lambda x will be equal to 0 at x equal to 0. load on each rail equal to 350 over 2, 175. This force will be 175 kilonewton. Hence, Y maximum will be P lambda over 2K multiplied by A, the factor of lambda x. The factor of lambda x, A lambda x, will be equal to 1. This factor, the factor A lambda x, as we know, equal to e to the minus lambda x multiplied by cosine lambda x plus sine lambda x. Since x equal to 0, sine lambda x will be 0 and cosine lambda x will be 1. E to the lambda x, e to the 0 equal to 1. Therefore, A lambda x will be 1. Y maximum equal to 8.5 millimeter. M maximum, use the moment equation, minus B over 4 lambda multiplied by C lambda x. C lambda x. C lambda x also equal to 1. And here the result will be minus 30 meganewton millimeter. Hence, now to get the maximum stress on the beam, M maximum Y over I will gives us 360 Newton per millimeter square. This is for the first case. We learn how to use and apply the deflection equation of unlimited beam subjected to concentrated load, and also the moment. And where is the maximum deflection? The maximum deflection under the concentrated load directly, which means x equal to 0. And when we want to compute the factor of lambda x, A lambda x, C lambda x will be equal to 1. Now, for the second case, B, for the second case, for track with 2 axle, track with 2 axle. This is the rails. Here, the first wheel here, the second wheel here, the third wheel here, the fourth wheel here of a truck. The first axle, and this is the second axle. The total weight is 350. Therefore, we have to divide 350 over 4 wheels. Every wheel will have 350 over 4, 87.5 kilonewton. If we would take, for example, this rail, all this rail, they are similar, and it plots the rail here, and the force comes from the wheel here, the second force from the second wheel on the rail here, and name this point as A, this point is C, and the distance between these two forces between the wheels equal to 1.5 meter. Now the problem is compute the maximum deflection and maximum moment. The maximum deflection is under the force, as we know from the typical curve of deflection of a limited beam subjected to concentrated load. The maximum deflection occurs directly under the force P. This is the maximum deflection. But since we have two forces, for example, if we take everyone individually, maybe the deflection curve like this. But because we have two forces, we don't know, maybe the deflection at this distance, this region, this zone between two forces maybe is greater than under load at point A or under load at point C. So we have to take another solution of computing the deflection at point B, and we are not sure that the maximum deflection at B, it may be between B and A and B and C. So therefore we have two choices now. The method of solution is to compute the deflection under the point A and C, they are similar, and the second solution is to compute the deflection at point B, and then choose the maximum between these two choices, between these two solutions. Practically this method is accepted. We can use a program to compute deflection at any point between these two forces. So let us now take the first choice. First, we will compute the deflection at point A or at point C due to load C, or at A due to load A, and then compute the deflection due to the load at C. So first, the distance will be x equal to 0, since the point is directly under this load. And in the second, the distance will be 1.5, since we want to compute the deflection due to the force at C. So now we have to compute lambda x at C. Lambda x at C will be lambda multiplied by distance x at C, x between C and A. This is A, point A, and this is point C. We want to compute the deflection at point A, but due to the force at C. The distance here is 1.5 meter, so therefore we have to use x equal to 1.5 meter. Lambda x will be 2.184. Then use this value in the equation of a lambda x equal to e to the minus lambda x. Here you can use this value directly in this equation, e to the minus 2.184, and cosine also 2.184 plus sine 2.184. But in your calculator, please change the system to a radian system. If you want to use it in the same system in degree, you have to change the value of 2.184 to degree. 2.184 multiplied by 180 over pi. Change it to degree. Then you can use your calculator in the degree system. After computing a lambda x, now replace a lambda x in this equation. A lambda x at C multiplied by p lambda 2k. We will get the deflection at A due to the force at C, plus p lambda over 2k multiplied by a lambda x at A, which is in this case x equal to 0, A lambda x will be equal to 1. So the maximum deflection is deflection. Now we assume the maximum deflection is at point A. So we have to compute deflection at A due to the force at A plus deflection at A but due to the force at C. Here the force at A and here the deflection at A but due to the force at C. This method is called the superposition method. In the superposition method, we can compute the deflection for various type of loading. So now YA will be 436 millimeter, and this value similar to YC. Also Y at C, the deflection at C gives us the similar value, but because we want to use X in a positive, not in a negative, because the formula don't take the negative into consideration. This is the first solution. The second solution is to compute the deflection at B between A and C. Here this is point A and there is force here, and this is point C, there is force here, and we want to compute the deflection at point B. So we have to compute Y at B, but due to force at C. And with respect to force at A, we have to multiply this value by 2. Since from B to A, this gives us X positive, but here X is negative, and negative X is not allowed to be used in the equation of deflection. So we have to compute the deflection at B with respect to C and then multiply it by 2 since it is the same. So now X will be 750 millimeter, 0.75 meter. Lambda X from C to B will be lambda multiplied by lambda multiplied by X, 1.092. If we want to use in degree, we have to multiply it by 180 over pi. This gives us 62.75 in degree. A lambda X e to the minus 1.092. This value will be the same for if we use the system of radian in calculator or even in degree. If we use the degree system, we have to use 62 here and 62 here. This gives us 0.452. This is the lambda at or A lambda X. Now substitute this value in this equation and multiply the result of deflection by 2. Here 87.5 and 2 times 15, and here 2 times 0.452 multiplied by P lambda. Some of books use beta, some of books use lambda. So here 3.84 millimeter. Now compare this value 3.84 millimeter with the value of maximum deflection obtained by the first method, which is equal to 4.36 millimeter. Since this value is greater than the value of the second method, we have to choose the maximum deflection equal to 400.36 millimeter at either end, and in the same procedure you can compute shear force, you can compute moment and slope at any point as we learn here. Thank you.